Hello, I'm Dr. Pods, and today I want to talk about the time domain analysis of a simple RC circuit. So imagine you're trying to charge a capacitor. For example, you have an electric vehicle and you're trying to connect the battery to the rest of the system when you're starting it up. So you have a resistor here, you have a capacitor, and you have a voltage source. And you're trying to figure out how long does it take to charge this capacitor. So the capacitor has a capacitance of C, resistor has a resistance of R, and say we are using 12 volts just because it is a convenient number. So the basic equation for the capacitor is, of course, a differential equation. So the rate of change of the voltage d over dtu is equal to the current divided by the capacitance, or the other way around, we say the capacitance times the rate of change of the voltage d over dtu of t is equal to the current going into the capacitor. Now, we can also calculate this current because we have the voltage of the capacitor U and we have the resistor R there. We have our voltage source of 12 volts. So this current is 12 volts minus U of t divided by R. There we go. Nice, simple equation. We can simplify it a little bit by multiplying everything by R. Then we get rid of this fraction and we get RC times d over dt U of t is equal to 12 volt minus U of t. And we have eliminated the current. We have a nice, simple first order differential equation. And now you're going to say, that's great, but how do I solve a first order differential equation? There are a number of ways of doing this, but my favorite one is by far one called Ansatz, which means you guess the solution. How do we guess the solution? If it is a first order system, we know that the solution is an exponential function. So our Ansatz is U of t is equal to U infinity, so our stationary voltage, plus U naught times, and here comes the exponential function, e to the lambda t, where lambda is a parameter and t is our time. Now you can see we have three parameters in here, and that means we have essentially three unknowns. In order to find these, we need to insert this equation, this Ansatz, into our differential equation. So first of all, we need to find d over dtu, because we will need that. That's quite easy. U infinity is a constant, so that disappears. And the other part becomes U naught. The lambda is the inner derivative, so we need to pull it out, times lambda times e to the lambda t. Now we can insert this into our differential equation. So we get RC times U naught times lambda times e to the lambda t is equal to 12 volts minus, now we need to be careful here, U infinity minus U naught e to the lambda t. And this might look a little bit confusing, but actually all we need to do is find our three parameters, U infinity, U naught, and lambda, so that this equation is always true. And we can do that by looking at similarities on both sides. So first of all, we have this constant here on the right hand side, 12 volts minus U infinity. So from this here we can easily conclude U infinity has to be equal to 12 volt. Then this term disappears and we are left with the remainder of the equation, which is RC times U naught times lambda e to the lambda t is equal to, and then we have on the other side, minus U naught e to the lambda t. And again, we can make a very simple conclusion here. We can find that we don't know anything about U naught, because for any U naught this equation would be equally true or non-true, but we can find lambda because RC times lambda needs to be equal to minus 1, or in other words, lambda is minus 1 over RC. So then we have found lambda. Finally, we do need to find U0, and that depends on the initial state of charge of the capacitor. If we say the initial voltage of the capacitor is 0, we can go back to our original equation here and say U0 is equal to 0, and from this it follows that U0 is equal to U infinity, minus U infinity, so minus 12 volt. Now we have all the pieces in order to write our solution. We have U infinity, we have U0, and we have lambda, so we can write down our solution equation, which is therefore, looking at our ansatz here, U0 of t is equal to 12 volt minus 12 volt times e to the t divided by RC, and we have to remember the minus sign. That is the solution, and that describes the charging behavior of this capacitor over time. If you want to know when the capacitor is charged, you would typically go to 2, 3, or maybe 5 time constants, and then you will find that if you plot this on a computer, you get a curve that looks roughly like so. So time is here, 12 volt is here, this is U of t. We start at 0, we will eventually asymptote to 12 volt, and so we get an exponential function that looks roughly like so, with the time constant being about here. So this is about tau equal to RC. And that's all there is to it. Now we can find out when the capacitor is sufficiently charged, and so we can analyze our system and make sure that it is suitable for our purpose. Thanks very much for listening, and please have a look at my other videos on YouTube.